Welcome back to Urbit from the Outside In. This is episode 4. In this episode, I'm going to describe Hoon, Urbit's programming language, the Arvo kernel, which is the kernel of the Arvo operating system, and the vanes, V-A-N-E-S, which are Arvo's kernel modules. So I'm really going to describe sort of all of kernel space, which, for those of you not familiar with operating systems, just means all of the code that is part of the system, part of the kernel of the operating system. So basically, the operating system code, as opposed to the code that the operating system is running on behalf of a user. So this is in contradistinction to an app, which might be a program on Unix or Windows, in Urbit we talk about GAL applications. We usually call them agents, but sometimes we use the term app for short. Thinking of it as a system, thinking of a GAL agent as a service or as an agent is really more applicable than thinking of it as an app, like an iPhone app. But there is some crossover. So I will be a little bit sloppy in my terminology there because ain't nobody got time for that. So I'm going to start by describing Hoon, our programming language, how that layers over Nock, what its design goals are, how it gets used in the system a little bit, and then I'm going to talk about Arvo, the kernel, so what its responsibilities are, and then I'll talk about what the actual kernel modules are, the vanes, and how Arvo interacts with those a little bit. But I'll just go through each one of them. There are 8 of them, so then by the time I get through that, that'll be a pretty complete description of kernel space as opposed to user space. And then in the next episode, I think I will end up talking about apps, GAL agents, and their interface to the kernel and how they work and how we think about that. Okay, so let's get started. Hoon is the name of Urbit's programming language. It's named after a line in a poem by Wallace Stevens called Tea at the Palaz of Hoon. Honestly, I've never really understood the poem, but I had actually heard the poem before. One of my friends recited it to me years ago before I even heard of Urbit. It's pretty well known among people who like poetry, I guess. Anyway, Hoon is a statically typed, purely functional language, and it's probably best considered a statically typed Lisp, although it's very different from other languages in the Lisp family. If you're not familiar with programming languages, don't worry about this. You don't need to know the history in order to understand what Hoon is like, what it's for, and how it fits into Urbit. So the general idea of Hoon is that Nock is a good machine code for Urbit. And if you haven't heard about Nock, in the previous episode, I went and described it from memory. I actually made a mistake in describing it from memory. So if any of you find the mistake, I will give you a planet. So the first person who finds the mistake and tells me about it. So there's a little reward. It's a minor mistake, but a mistake nevertheless. So last episode I described Nock. In this episode I'm not going to describe it again, but other than to say that Nock itself is not designed to be, a pleasant environment to write programs in directly. That's not the point. It's supposed to be something that a machine can run pretty easily. And so, in order to actually write Nock code, you don't want to write Nock code itself. You want to write code in Hoon, which is designed to be pleasant to write programs in. And then there is a compiler that translates Hoon into Nock. So the compiler is a function. and you give it some source code, some Hoon source code. It's just a bunch of text, and that will compile it to Nock. So how does Hoon work, right? What does it do? And the first thing it does is it starts by naming parts of Nock, right? In Nock, everything's a number, including various slots in the tree, right? Various locations in the tree, like each one of those is a number. So if you're going to try to write Nock code that references other Nock code, which you always do, right? Because you end up building up lots of routines that you can call, and lots of other kind of layers of a system, layers of abstraction that you build. And so in order to refer to those in Nock, you have to refer them by number. And you don't want to have to remember all those numbers as a programmer. In general, people don't write complex systems in machine code. You can, but it's not fun. And in particular, you should be able to get just a sort of programmer productivity improvement by using a higher level language that compiles down to the lower level language. And part of that productivity improvement comes from just being able to refer to things by name. So you can give a textual name to each part of the tree. And the other thing that Hoon really does, there are a couple of other things that Hoon does for you. I'll go through these in more detail. It starts by naming parts of Nock, and then it also adds a lot of syntactic sugar for common operations. So that means they're like special pieces of syntax, like special little symbols that you can use that compile down to more complex Nock expressions that are common patterns. It also adds a bunch of miscellaneous facilities, like how to print data structures for debugging and for inspection of the system. Stack traces, so like printing a trace of what went wrong if there was an error. And a bunch of facilities for systems programming, so running other code. And also operations for dealing with data types. So I'll describe the idea of a data type, Hoon's idea of a data type, how we use it. But okay, so that's going to be that's the outline for Hoon here. I'll start by naming. So every slot in a tree has a number, right? It starts with 1, and then 2, 3, and then 4, 5, 6, 7, etc. as you go down the tree, starting at the root, left to right. And in Hoon, you can name any part of that tree, and that's called a face. You give it a face. And so this is like, and then you can refer to a part of the tree by just using that face, using that name, and that will do a Nock 0 to load that part of the tree. But that's actually only one kind of name. You need another kind of name too, which is a name for arms. If you recall, in one of the previous episodes, I described how the basic organizational unit of code in Nock is a core, which is a pair of code and data, where the code is a bunch of arms in the head of the cell, in the head of the core, and the data is in the tail of the cell. So in Hoon, each of those arms, in addition to having a number, which is the slot where they live, inside of the head of the core, you actually just define them by name, and it's like defining a function or defining, right? So you name that arm, and then the Hoon compiler will compile that down to a particular, a battery, a tree of arms in the head of the core. And so as a Hoon programmer, you don't have to remember what number, what slot you don't ever have to know what slot the arms get compiled down to. So in general, Hoon still exposes operations for looking at a tree as a tree shape, because you do end up doing that a fair amount. But you can also add a name, a face, or an arm name to each part of the tree. And so you don't have to be sort of doing direct tree manipulation in Hoon all the time. You can just use names, and those names behave very similarly to the way they do in other programming languages. So this is sort of most of the difference between Hoon and Nock, actually. And then the other big difference is that so Nock has basically no syntax. There's a little bit of syntax for sort of implicitly in the way we define it, where we say, okay, we'll use brackets to describe cells, and we'll use decimal numbers to describe atoms. But that syntax is arbitrary. It's not really part of Nock. Anything that would let you describe a tree of numbers is a valid syntactic representation of Nock. Hoon is not that way at all. Hoon, a lot of what Hoon does for you is add syntax. And it's very specific syntax. It's done in a very specific way. And that way is intended to maximize the ability to make the language convenient. That's what the syntax is for in Hoon. So it's a very regular syntax, which means that almost all of the operations that you can do, any kind of Hoon expression, starts with a rune, which is a digraph, fancy name for two characters, and they're two symbols. So basically, it's the if you hold down Shift and use one of the number keys, any kind of sequence of two of those is going to be a Hoon rune usually. And there are quite a few of these. There are something like 100 Hoon runes. Sounds like a lot. It sort of is a lot, although they're categorized by the first character, and that helps a lot. And then also, you can't ever add more of these, and so there's some upfront investment in learning these runes, but then once you learn it, you're done, and then you can look at any Hoon code, and it's very clear what it's doing. So this sounds harder than it is, really. It takes a little bit of time to get used to all the runes, but they're typically used in context, and so you even if you just remember those 10 or so categories of rune, when you see some rune that you don't know, but you know what category it's in, generally you can infer what it's doing from context, and then that also helps you learn them. Some people find this more difficult than others, but in general, I think the runic syntax is one of the most successful parts of Hoon. Almost everybody who spends a little bit of time with Hoon ends up learning the runes and then finds the language very easy to read as a result. So I was saying that this is syntactic sugar. So a lot of these runes, so each rune starts some sort of expression, and it might have some number of other sub-expressions within it. So I think a good example is the tis-faz rune, so equals and then slash. By the way, each of these, so you notice I said tis-faz, that's because Hoon is the world's only spoken programming language. Seems like a sort of obvious thing to do, but it's, as far as I know, no other languages actually do this. But in Hoon, every symbol has a canonical pronunciation. So the equals sign is pronounced tis, the forward slash is pronounced faz, and they all have one syllable pronunciations. And so this makes it very easy to discuss Hoon. You can actually just read it to each other, even in, say, a remote call. Now that we live in a remote work world, being able to pronounce code to each other is more useful than you might think. It's one of those things that once you get used to it, the idea of going back to Earth programming, where you can't even pronounce things to each other in a succinct and canonically understood way, it just seems completely insane. Anyway, the tis-faz rune is a good example of a rune because it compiles directly down to a Nock 8. So a Nock 8 is it's a way of declaring a variable, basically, as I described in the last one. So it says it takes two subformulas, right? So the knock8 is a formula, and it has two formulas inside of it. One that says run this formula against the subject to produce a new variable, basically. And a second one that says, okay, run the rest of this code against a modified subject that has that variable pinned to the head of it. So you take the old subject, and then you make a new subject by making it a cell where the old subject is the tail and the head is the result of running that first sub-expression against the old subject. So it's saying, okay, let's run an expression and then store the result, right? So pin that by prepending it to the subject. And so now then we want to run some code that has access to the previous subject and also has access to this newly declared variable, right? And it's just sort of a structural way of expressing that intent. So that's a knock8. And the tis-faz rune in Hoon compiles down to a knock8. That's what it is. And so it also has, it actually has three sub-expressions, because the first sub-expression, instead of two, because the first sub-expression says what name to give it. So you might say, tis-faz foo, 3 foo. And that will produce 3 when you run it. Right? So it's saying take the expression 3, take the result of that, store it as foo, and then the last sub-expression says just return foo. Now you can imagine 3 and foo being more complex. 3 and the last sub-expression there being more complex. And they generally are. But so the only major difference between tis-faz and knock8 is just that tis-faz gives you a way to name the result of this operation so that you can name this new variable that you've created. And that's pretty much it. You can also specify a type of that variable, and I'll get into the types in a little bit. But in general, all of the knock operations, all the knock opcodes have runes that compile down to them. And then there are some Hoon runes that compile down to sequences of knock opcodes, or sort of more complex layerings of those. So there are a bunch of, for example, Hoon runes for declaring a core. And a core is something that knock sort of implicitly understands, but there's no explicit definition of a core in knock. And so, that's not really using, that compiles down sort of indirectly to some knock opcodes when you declare a core in Hoon. So that is sort of more machinery in Hoon, but it still produces this very simple structure, right? Where so the Hoon that you write to declare a core, these are all the runes that start with bar, by the way, the vertical bar. Every rune that starts with bar declares a new core. So you can declare a gate, which is a function with one input, using bar tis, right? Bar equals sign. Bar dot describes just a core with one arm that you can, just a core with one arm that you can fire. So it's like a way of doing what's called a lazy evaluation. You can have a bar cab. Cab is underscore. Bar cab is a core that has a sample that you can replace with a new argument, just like a gate. But it also, instead of just having one arm like a gate, it has multiple arms. So that's like a state machine or an object-oriented programming. Basically, most programs that you think of as a program that has some state that gets run, where it gets like a new event injected into it each time, and then but then there are multiple things that you might want to ask it to do after injecting that event. That's going to be a bar cab. There are a few other ones too. The simplest one is bar sen, where sen is %, and that just says, declare a core with here are the arms, and that's it. It should be noted that when you declare a core in Hoon, it actually declares a core that wraps around the existing subject, and uses that existing subject as a context so that you can still call all the routines that you have defined already. And so you're basically just adding new capabilities to this program when you sort of wrap a core around it. So a barsen actually produces a core that has as its battery all the arms that you define inside of that barsen expression, but then the tail of it is a context that contains whatever was in your subject at the time that you declared that core. So in general, the Hoon programs kind of stack cores on top of each other. And we'll see it when I describe compilation and building, right? Like, what is this process that the system uses to generate a knock program from some Hoon code? It takes advantage of that process of stacking cores on one another, because we'll actually, sort of each layer of compilation typically will stack another core, in the head of the previous expression. So the compilation discipline that we have, the building discipline, pretty closely reflects the actual structure of programs. It's pretty nice. Gotta say, it's pretty nice. So there are other, but yeah, most or a lot of Hoon runes just compile down directly to knock expressions, to knock opcodes. So the Tizgar and Tizgal runes compile down to knock 7. The Whatkol rune compiles down to a knock 6 very directly. And there are lots of examples of this, actually. So, and how are these syntactic elements chosen? It's like, well, they're the ones that are just convenient to use, right? It's like, because you don't want to be writing a lot of boilerplate code that's sort of very repetitive and tedious. And so you don't have to do very much of that in Hoon generally. You can usually just kind of write what you want to write, and the runes are high level enough that despite knock itself not being very high level, the runes give you a sort of nice high enough level interface to knock that you don't have to write a bunch of tedious repetitive code typically. So, and then the other nice thing about the compilation step from Hoon to knock is that it's extremely straightforward. There are a few runes that have some non-trivial complexity where the way that they get compiled, it might actually be 5 or 10 lines of Hoon in the compiler that determine how that gets compiled, but most of them extremely straightforward. Now there's more complexity in the Hoon type system, which I'll get into next. So a lot of the compiler has to deal with checking types and making sure that the types are legit. But the actual code generation process is almost completely trivial. And so this makes it very, like, when you look at a piece of Hoon code, you know pretty much exactly what knock is going to come out of that. And that's a nice feeling. You don't really have this feeling of like undefined behavior like you might in C, or just, also the Hoon compiler is not an optimizing compiler. So it doesn't apply optimizations the way a lot of compilers do, because you don't really need them. And because it's such a low, thin layer over knock, that there's not that much that you would even want to optimize out. You can imagine doing some, but that those kinds of optimizations are probably best done in the knock interpreter itself, which is outside of the system, right? So in general, in Urbit, we try to have the formal specification for something be written inside the system, and then if there's some sort of open-ended optimization problem that could continue to where you just want it to go faster and you want to do more and more tricks over time to make it go faster, it's like, all right, well, that doesn't really belong in the spec. So do that in the runtime. And so that's what we do. The knock interpreter itself is actually, it has a couple of tricks up its sleeve that it does to make knock go faster. And we don't need to put those tricks in the Hoon compiler, which is part of the system. So the Hoon compiler, it's a function from Hoon text to a knock data structure. And the Hoon compiler is itself written in Hoon. So it was bootstrapped a decade ago. So the process of bootstrapping a compiler or self-hosting a compiler is where you first write it in some other. Is when you have a compiler that translates the language that it's written in into some other language. So the Hoon compiler, which compiles from Hoon to Nock, is written in Hoon. Well, how do you get there, right? And the answer was it was originally written in C, and then pieces of it were written in Hoon until that connection to C was completely discarded, and now the entire thing is written in Hoon, and actually has been for many years. One thing I should mention about Hoon, by the way, is that this every Hoon expression compiles down to a Nock formula, right, which is a function that runs against the subject, right? So every piece of Hoon gets compiled against a subject type. So it's sort of every Hoon expression is sort of only meaningful when compiled against the type of a subject that it will run against. So then you will compile the Hoon down to a Nock formula, and that formula will run against the subject of the same type as that Hoon was compiled against. So I think that I'll touch back on that in a minute because I don't think it's that clear the way I described it. But let me describe the idea of a type in Hoon, and then I'll revisit this and it'll make a little bit more sense. So in general, in programming, the word type can it means like it can mean a few things. In Hoon, it really describes a type is a description of a tree, many trees, and so you can think of it as it's a way of describing a tree. So, and it generally includes the shape of the tree. So saying like, okay, well, it's a cell, or it's a cell of an atom in a cell, right? So that in fact is a Hoon type. Cell of atom and cell of noun and noun. That's a valid Hoon type. So in this case, we're using the type is actually a Hoon data structure, right? So it's a Nock tree. It itself is represented as a noun, just like everything else. But that noun is like a schema for describing the shape of some tree. And so some trees, some nouns will conform to that shape, and others won't. So you can also think of it as a predicate. So a function that produces a Boolean saying yes or no, does this tree fit into this shape? Now it's important to note that just because you have that predicate doesn't mean that you can always check. So it's not necessarily a function you can run, but if you have, let's say, a pair of a noun and its type, and in Hoon we call this a vase. We use this a lot in the system. So a vase is it's a cell where the head is a type. So it's, some data structure like, a cell of noun and noun. And then the tail is just some piece of data, some noun. But there's a constraint that the tail has to actually match the type, has to be a value of the type that's described in the head. So in the tail for this particular vase, you would have to have, a cell of noun and noun in the tail in order for it to be a valid vase. If the type in the head says that it's a cell of noun and noun, then the value in the tail should actually be a cell of noun and noun. All right, so that's a vase. And so this is like one of the most common ways that we use the Hoon type system, is by passing these vases around that were generated by the Hoon compiler. And so it's basically saying, okay, here's this piece of data, and we actually know that its type is this type that's described in the head. And so then that allows us to combine those pieces of data, because now each vase is sort of self-describing. And so now we can just sort of do operations that combine those vases. So for example, by compiling a program against that vase. And this is sort of the fundamental way that we combine pieces of code and combine pieces of data in the system, like in the kernel, is by doing it with vases. I'm sorry that this is kind of it's sort of advanced in some sense, right, to talk about types from this perspective. And so I kind of ask for your forbearance here, and I'll try to make this sort of make more sense as I go through more of how we use vases and how we just, like, in general, how we use the systems programming stuff in Hoon to generate programs, to run programs, to check types, that sort of thing. But I think that, keeping in mind that it's mostly used, that the type systems are mostly used in this vase way, I think is going to be helpful for understanding sort of what is a type. So first I've said that a type encodes the shape of a tree, but it also encodes all of the names that have been given to that part to various parts of the tree, right? So if I do, and so this is how you can use this type as a way of describing the subject against which a Hoon will be compiled, because the overall kind of compilation paradigm is to say that we have a vase of a subject, and there are actually kind of multiple stages here of compilation. So basically, the general idea is we start with something like a standard library. So that might be Hoon.Hoon, the file that describes sort of the Hoon standard library. Or it might be Zeus.Hoon, which is the file that describes the standard library that's used by Vanes and user space. Both of these are cores. And let's use Zeus as an example. So Zeus has just all kinds of helper routines that you might want to use in an application, right? So stuff for dealing with HTTP requests and converting between different data types, and some common data structures that you might want to use in your application. So there's a core with arms defining all these things, and the system stores a vase of that core. So it stores, again, a cell where the tail is the core itself, and the head is a type saying this is a core. Here are the arms. Here are the return types of all the arms. So when you run this arm, what type will that arm produce? So generally, when I want to build an app, right, a user space application, a user space agent, a Gall agent. So for example, Landscape has a bunch of, which is the user interface that you use when using Urbit, that has a bunch of Gall agents in it. So there's one for chat. Right? Chat is a Gall agent. And so when I want to compile chat or build chat, let's take a simplified example of this where, let's say it's just one Hoon file. It's not, but but some apps are. And the general principle holds, which is that I take that Hoon file, so that's some text, and then I compile that against the type of Zeus as the subject type. Because what I want to do here is I want to say, okay, this app uses routines from Zeus, right? So it has to actually have the Zeus core in the resulting program, right? So we're going to produce a new knock program, and this knock, which will be the app, and this program will have a bunch of its own arms, right? So things that it can be asked to do, right? Routines that it can be asked to run. And then, when it goes to actually, run then the definition, the code inside of those routines will actually need to be able to call into common standard library routines that are defined in Zeus. And in order to do that, we actually have to have the Zeus noun, the Zeus core, inside of our app so that we can call it. For those of you worried about memory, by the way, the system deduplicates, or it just doesn't bother creating a second copy of the Zeus core in memory. So even though it's logically inside of every app, it only takes up, it's only there once in memory. It's not duplicated in memory. And so for those of you who are more familiar with sort of C and systems programming, there are multiple pointers to that Zeus core. But it uses, Nock in general uses what's called structural sharing, so that you can have as many copies as you want to a big noun, and that doesn't use much more memory. So just for the people waiting to jump in with a criticism, that one's not a big problem. Okay, so but in general, we want to actually have this Zeus noun inside of our app, so that the app can call into the routines that are there. Which means that when we compile the app is going to have references to arms and Zeus, right? So let's see, what's a good example? There's a format core in Zeus, for example. And so you might, in an app, see calls to format, which is something for, a bunch of routines for, formatting data to HTML and whatnot. And so, in the code for the app, right, this Hoon file that defines the app, all we want to have is, we just want to call the format, call some arm in the format core by name, say format. And so in order to compile this Hoon, you actually have to give the compiler a type, and that will be the type of the Zeus core. And so that way, when the compiler sees a reference to format, it can look that up in the type of the subject, which is Zeus, and that'll resolve to like, okay, well, there's an arm at slot whatever 42 or whatever it is, right? And so that, but if you compiled that Hoon against a different subject, let's say something else that had a format core at some different slot within it, then it would compile down a different Nock, right? So compile it, because it would end up resolving that reference differently, right? Resolving that variable to somewhere else in the tree. And so and actually when the compiler runs, it produces, so you give it some Hoon text and you give it a subject type, and it produces a cell of the type of the resulting program, and a Nock formula that can be used to run against a subject of that type to produce the resulting program as a Nock core. So this is actually, the compilation there is really just the first step of producing this program. And the second step takes the Nock of the result of compilation, which is a formula, right? So it takes this Nock formula and actually runs it against the Zeus core, right? Because we have a vase of the Zeus core, which is the type of the core and the actual value of the core, right? There's like the actual Nock core, as a noun sitting there. And so we can use that as the subject and use the result of compilation of this app as a formula. And we run the formula against that subject. So we run this Nock formula as the result of compilation against the actual value of the Zeus core. And that will produce a new app core. And that app core is basically going to be, a core that has some arms in its battery for doing app stuff, right? The things that you can ask an app to do. And then in its tail, it's going to have potentially a bunch of other stuff, but at some point at the far right edge of its context, it will have the actual Zeus core against which it was compiled, so that it can call into that. And so there are two steps, right? So first we run the compiler, which gives us a pair of type and knock, and then we execute that knock against the value of the subject, the value of the Zeus core, and that produces a value of this new program, right? This new app. And so now, after we've done both of those things, we have a vase of the app core, right? So we have the type of the app core in the head, and then the app core itself in the tail. And so you can think of Hoon, and one way of thinking about Hoon is that it's a way of transforming from one vase to another vase, right? Because we started with a vase of the subject, or the vase of Zeus, the compilation subject. We compiled the Hoon against it, and then we ran the resulting knock against it, and that gives us a vase of the result of running that Hoon. So actually, when you think of there's this sort of two-step process. It should be kept in mind when you see like a Gall agent, the code for a Gall agent, because what that code is doing is it's saying, here's an expression that when you run it against the standard library, produces a program, right? It returns a program. It constructs the program and returns it. And this can be layered recursively, right? I mean, you can do sequences of these, as you can imagine, right? Because, okay, we go from vase to vase. Like, well, you can you can do that again. Run another Hoon, and right, another piece of Hoon, and add to that stack. Or it doesn't necessarily have to add to the stack, right? Like in this case, we're using it to produce a program, but you could use it to just produce the vase of a piece of data. We do that sometimes too, right? And so you could even use it to produce a constant, right? So let's say that you have a Hoon where the text is just 3. Maybe I should have started with this because this is sort of the trivial example. So this is saying, okay, no matter what the subject is, produce a constant, right? Just produce the value 3 as an atom, right? And so, well, what's a formula? So this has to compile down to a formula, right? Because every Hoon compiles down to a knock formula. So in this case, we want to compile down to a formula that says, I don't care what the subject type is. We're not going to look into the subject at all. We're just going to produce the value 3 no matter what. So that corresponds, if you recall, to a knock 1 opcode, which says exactly that. It says ignore subject, produce whatever is inside, produce this constant value. So sure enough, if you write 3 here for Hoon, that will compile down to a knock formula of cell of 1 and 3. That's it. So, and there are actually plenty of examples where you want to ignore the subject and just produce some constant. So actually, the Hoon compiler is defined this way. The Hoon compiler ignores whatever subject it was compiled against, and just produces a constant of the Hoon compiler as a program. So it builds up everything from scratch, which is what it needs to do, right? Because that's the thing that bootstraps the rest of the system. But if you're an app, then you actually need to care you need to care about the subject, because you want to use a bunch of routines that are defined in the subject. So now you might start to see why we call this subject-oriented programming, right? It's because we want to have all these stored routines, and then we want to be able to and type definitions, right? Definitions of data structures that we can use, and names for various common routines, right? Pieces of functionality that we want to be able to reuse, and then that we have to sort of treat that as a piece of data, right? It's because it is a piece of data. It's code, but everything is stored as data, right? Everything is a noun. And so, now we have this very kind of nice little language for manipulating programs, right? For taking a program and building a more complex program out of it that uses it, right? So an app that uses Zeus, for example. So this is part of what I was referring to a little bit as the systems programming facilities of Hoon, right? So Hoon is designed to be a systems programming language, which means that so like C or C++ are systems programming languages, which means that they're code that's designed to let you run other code and manipulate other code. So when you're writing an operating system, and Urbit from this perspective is very much an operating system. The only difference really between Urbit and traditional operating systems, as I mentioned before, is that Urbit does not have a hardware abstraction layer. So it's not, it doesn't specify how you communicate with various, input-output devices, except at a very high level. And so, but from the perspective of, but the other thing that operating systems do is they run other code, right? So that is very much what Arvo does. And so Hoon, as a language, different programming languages are designed for different purposes, and Hoon's primary purpose is being able to run other Hoon code that's compiled to Nock, and being able to compile and build other Hoon code. So most of its sort of design decisions are geared towards that. So by the way, I mentioned that the when we go to build an agent against Zeus, we compile it, and then that produces some Nock, and then we just run that Nock against the value of the Zeus core. This is what we call running raw Nock, because, and this is something that Hoon lets you do. There is the .tar rune, so dot and then star, asterisk, and that takes two sub-expressions, one of which is gets evaluated to a subject, and the other one gets evaluated to a formula, and then that will actually run that formula against that subject. So you can just call into Nock directly from Hoon. So this is something that is one of the major it's one of the most important things that Hoon needs to be able to do, because a lot of times the system doesn't know the type of what it's going to run, so it can't run sort of Hoon code in a typed way. And so it might just need to run some Nock, even though it doesn't know what that Nock is. So it just knows, well, okay, here are some nouns, run Nock, get a noun out. And so the type system uses what's called subtyping, which means that you can have a type noun, and you can also have a type atom and type cell. And if you know that you have a cell, right? If you have a type cell, you know that that's a noun. And similarly, atom is also a noun. And if you think about it, a cell of atom and atom, you know that is a valid cell of noun and noun, right? It's just more specific. And so a subtyping language like Hoon is one where the type system actually understands this. So the Hoon compiler knows that a cell of atom and atom is a valid cell of noun and noun. And you know that an atom is a valid noun. A cell is also a valid noun. Of course, it also knows that an atom is not a valid cell, and a cell is not a valid atom, because those are not subtypes of each other. Those are different, right? But atom is a subtype of noun, right? So basically every atom is a noun, but not every noun is an atom. Similarly, every cell is a noun, but not every noun is a cell. So atom and cell are both subtypes of noun. And I think this is illustrative because it illustrates it demonstrates what how we use the type system, right? Because we might, for example, run some Nock that produces a noun, and we don't know anything about it other than that it's a noun. And so we need to actually be able to sort of inspect that noun. And as we inspect it, we want to learn something about its type. So we want to be able to assert, for example, we might want to be able to say, this is an atom, not a cell. And once we assert that it's an atom and check it using knock3, then if it passes the check and knock3 comes back and says, yeah, it's an atom, then, okay, well, now we want to be able to represent that in the type system and have as, okay, this is actually an atom. We know it's an atom now, right? So it's sort of like using the type system to refine our understanding of some noun and say, okay, well, we know that it's not a cell, right? We know it's actually an atom. So there is there's a whole system in Hoon for that lets you write functions that take in any noun and coerce that noun into a particular type. Coercion here meaning that if that function returns, then it'll return a value of some more specific type, like coercing to atom from noun. And then if you run that function on a noun that isn't actually an atom, then that function will crash. And so this is a way of sort of refining our understanding of what the type is. And so we call this function a mold, because the idea is it's sort of molding its input. In Hoon, actually, this is the typical way of declaring a type, and there's a bunch of syntax for declaring molds. So there's one that says, so the pat symbol is, atom. The ket, the pat is the at sign. The caret is cell. And then there are ways of combining these to say, so there are other runes for combining, a cell of an atom, etc. And you can also define core types this way, which include, so any type that includes code is going to be a core type of some kind. And we can also do recursive types, such as list. So you can say list of pat for a list of atom, right? And that's a bit more complicated. That uses a system called wetness, which is a way of defining functions that are very similar to what's called parametric polymorphism in traditional programming languages. And again, don't worry about that, but it basically just means that, let's say I have a function that wants to reverse a list. In Hoon, that's called flop. Ideally, you can pass in a list of atoms, and then it'll return a list of atoms. But if you pass in a list of cells, it'll instead return a list of cells, right? And so the return type of that function isn't just, the whole type of that function, the type signature of it, it takes in list of x and then produces list of x, whatever x is, but x can vary. So this is called polymorphism, right? Because the multiple shapes, right? Because it can take in a list of any tree shape and it'll produce a list of that same tree shape. And there are a bunch of other examples where you want to have routines that are generic in this way, but that preserve type information so that it doesn't just say, okay, well, it can take in a list of whatever you want, but then the result is just going to be list of noun, and we've lost whatever specificity we've had about each item, where, the input, it would be bad if that happened, right? If you passed it in a list of atoms and it came out as just a list of nouns, like, okay, well, that's less useful now, right? Like the type, the compiler used to know that every item in this list was an atom. It would, it's very inconvenient if it loses that information. So wetness is a system for letting those types become polymorphic. And this is probably the hardest part of Hoon to use, is the wetness system. And in practice, so if you need to define your own, wet gates or wet cores that have this property, that can be tricky. Especially if you try to make it really kind of smooth to use. And so this is probably the hardest part of Hoon to learn. But fortunately, generally, it's actually pretty rare that you actually have to write one of these yourself. So, you can use the list routines that are wet. And you don't have to know too much about how how the compiler actually deals with this stuff in order to use it productively. The one thing I will note is that because Hoon is a subtyping system, if the type that you pass in to, say, flop, isn't actually a list, it's just something that's a subtype of a list, such as like, such as the, atom, 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 null, right? That does nest inside list of atom, right? It is a subtype of list of atom, but it looks pretty different to the type system. So the type system will be able to say that it is a subtype of it, but it won't be able to run, this function that's designed to run on lists and figure out like, oh, this is actually a list of type atom, because it doesn't really know that. And so so often you have to cast the input to a list. So there's a rune, the kethep rune. So caret dash caret hyphen that will cast something to a list. So when you cast, that says, okay, well, this is going to run at compile time, and we're going to deliberately lose some type information. We're going to say this is just an instance of a more general type. But in this case, with wetness, sometimes the compiler needs to know that it is actually a more general type, not something more specific. And in general, with Hoon, there's what we call the TMI problem, too much information. So often, if you're writing Hoon, you're having some trouble, you might need to cast a more specific piece of data to a more general one in order for these sort of routines that are designed to run on general pieces of data to actually work. This TMI problem is actually not nearly as bad as it was several years ago. And there are a couple more improvements that we were going to make to the wetness system, I think, to make that a little better. But that really is the rough edge of Hoon. So that's the hard part to understand, is exactly how wetness works. And yeah, the general advice I always say is to fix it fast, add a cast. That's almost always the way of getting out of these issues. So fortunately, it's easy to fix once you're used to it in most cases. But yeah, that's the hard part of Hoon, and wetness is done in this way because for a few reasons. One is that we have to know that it compiles down to the right knock. And then there's this sort of general issue with subtyping, where like, based on what Hoon needs to do, it's very, very convenient for it to be a subtyping language, right? For you to be able to say like, okay, yeah, this is a noun, and then a cell is actually a subtype of a noun. It's a very natural thing to do, and you might actually be very surprised if you go and use some other languages that typically are not subtyping. But yeah, one of the downsides is that it makes this wetness stuff harder. It makes it harder to do these sort of generic routines. So that's the trade-off that Hoon makes. Why was I talking about wetness? Well, that's a big disclaimer, really. I think that's probably the hardest part of the system to understand, maybe even in general. I think wetness is really the toughest. I said in the last episode that there's no rocket surgery in Urbit. I think this is an exception. There's some rocket surgery going on here, and I think we could do a better job of reducing the amount of rocket surgery involved. But just full disclosure, it is kind of tricky. Although I will say, as I mentioned before, that in practice, when you're using these routines, it's not that tricky typically. It's mostly just when you're defining them. So, I've discussed some basics of the Hoon type system, the way that it uses names, right? It names parts of the tree, and a little bit of the system programming facilities, where I mentioned that we can run raw knock. So this knock runs and this is why I was talking about wetness and whatnot, because I was talking about subtyping. And one of the big reasons we need subtyping is because often we end up running some knock code where we don't know anything about the type, or receiving a noun from the outside world where we don't know anything about the type. And so often there's this process of starting from just a raw noun where we don't know anything about it, and then using the type system to coerce it into a much more specifically typed value. It doesn't change the value, It just well, sometimes you want to change the value, but almost always you don't change the value. Just say it's just a way of sort of running assertions that let us, if once all those assertions pass, then we know that this is in fact of the type that we hope it is. So if I receive a noun from another ship over AIMS, Urbit's ship-to-ship networking, then I will generally coerce it into a data type where then I have names for all the different pieces of it. I know what shape it is, all that stuff. So that's usually the first thing we do when we receive a piece of unknown data is coerce it to a type. And that makes heavy use of the subtyping system. So there are a couple more things that Hoon lets you do that are in the sort of system programming vein. And they'll get used a lot when we run user space code. So usually when we run user space code, we could just run it as raw knock, but we usually don't. What we usually do is we run it meta-circularly, which is another big fancy word. But what it means is, and this is actually, I think, one of the coolest parts of Urbit, and it's a sort of, there's a profound beauty to it that, in my opinion, is something that Lisp, in all of its dialects, has sort of always been striving for and never really hit, and Urbit finally hits it. And this is one of the biggest reasons that I sometimes claim that Hoon is the one true Lisp, is because we can do meta-circularity. Okay, so what is meta-circularity? Hoon has a function called mock, not knock, but mock with an M. And that is a metacircular knock interpreter. So what it is it's a knock interpreter written in Hoon. So it's a piece of Hoon code, it's a function. And you give it the noun for a subject and the noun for a formula. And it interprets that knock expression. So it runs it. It runs the knock expression. So it has a code. So it looks at the formula. It says, is this formula, does it start with 0? Okay, well, then it's opcode 0. And so let's, grab this part of the subject, right, according to whatever knock, right? Is it a knock 1? Okay, well, let's, ignore the subject, just produce the tail of that, knock 1 formula, right? Just produce a constant, right? And so it just has a big switch statement, a series of if-else statements, checking what the opcode is, and then actually performing that opcode, performing that operation against the subject, and then sort of, does this recursively. Okay, so it's a knock interpreter written in knock, right? Written in Hoon, compiled down to knock. It's worth mentioning here that there is a distinction between compiler and interpreter. So a compiler is a program that translates a piece of code written in one language into a piece of code written in a different language. So the transformation from Hoon to knock, there is a Hoon compiler. So you give it Hoon source code, and that just it translates it into knock code, but it doesn't run it directly. Whereas an interpreter is something that just executes a piece of code in some language. So so var, Urbit's runtime, is a knock interpreter, where it just interprets the knock. Now, these are somewhat fuzzy distinctions, because if as an example of the fuzziness, the current var, its knock interpreter, the way it works is it actually first compiles the knock to a bytecode language, a different language that it can run more efficiently, and then it interprets that bytecode. But it's still an interpreter, because the thing that you ask it to do is to run the knock, and its implementation happens to compile that to some other language before running it, but it does run it. So it really is an interpreter. So this, similarly, mock with an M, written in Hoon, that is a metacircular knock interpreter. Metacircular just means it's an interpreter for a language that's written in that same language. Right, you can see the echo of this with Hoon. The Hoon compiler is a self-hosted compiler, which means basically the same thing for a compiler, right? It's a compiler for Hoon that's also written in Hoon. So mock is an interpreter version of that. It's a related concept. If you're really interested in the math behind these things, there's something called the Futamura projections, which we don't use directly, but it's a kind of fascinating look at interpreters and compilers and how those can be kind of combined and like run recursively against themselves, and you can do some really weird stuff. So once it's an interesting sort of facet of Turing complete systems, right? These sort of universal computing systems and universal languages that you can kind of combine them in these really interesting ways and transform them. So coming back to the subject at hand, we have mock, which is a metacircular knock interpreter. So it's a knock interpreter that is itself written in knock. And you might ask, like, well, why would you want to do that? Right? Don't we already have a knock interpreter? And the answer is yes. But doing it metacircularly lets us actually change knock a little bit. So instead of just running straight knock, we run a knock that actually has an extra opcode, a knock 12, which performs a scry operation. And this is actually managed by the Arvo kernel, generally speaking. But it doesn't have to be, but in practice it is. And so basically what that does is it says that code that's run metacircularly in this way, that's run by this interpreter, has access to this other opcode. And so if it runs that opcode, then this metacircular interpreter will perform a scry operation, which is a read. It'll do a read from the Urbit namespace. So I'll get into this a little bit later, but there's something that's sort of like a file system in this, or like a web URLs, except that every path, every scry path is immutable, meaning that it's always, if you ask for the data at that path, it will always give you the same result. This is important to maintain that property, and so we use that's part of the job of the Arvo kernel, is to maintain that immutability. But so app code, which is run metacircularly, whenever we run chat, that's run using mock, and so that allows the chat code to actually access this scry function, or to run it. It actually doesn't have access to the function itself, the code of the function. All it can do is say 12 and then some path, and then the metacircular interpreter will say, oh, I know how to run that, and it'll perform the query and return the result and then keep running. And so the other thing that this metacircular interpreter lets us do is catch errors. So something I haven't talked about with knock, although I've sort of alluded to the capability, is the ability to crash. So knock, in a mathematical sense, is a partial function, which means that from noun to noun. So that means that some nouns that you give it, it will actually return a value. But for some nouns that you give it, it won't return a value. And so for anything where it doesn't return a value, we call that a crash. And you can access this in Hoon. You can ask knock to crash with the zap zap rune, which is 2 exclamation points. So if you ever see 2 exclamation points in Hoon, that's zap zap, that means crash. If a crash happens at the top level, so if a crash happens in the kernel, in the Arvo kernel, then that kills the event. So if you recall from the previous, from one of my previous episodes, every Arvo event is a transaction. So it either completely happens or it doesn't happen at all. And so one of the ways that it could not happen at all is if it encounters a zap zap, which crashes, and then the interpreter says, okay, I'm not going to, that event didn't produce a new state and effects, so nothing happened. So it just goes back, it'll try the next event in the queue and run that instead. or actually usually it'll deliver an error message as a new event into Arvo first, which I'll get into when I describe Arvo. But in any case, at the top level, this crash will just kill the event because, yeah, this is a way of saying this function, the overall Urbit transition function from old state and new event to new state and effects, that failed to run, right? It did not produce a new value, so all right, we'll give up on that event. And there are actually two categories of ways this can happen: a deterministic crash and a non-deterministic crash. So a deterministic crash is a zap. They're basically the same thing. And what that means is that if you ran this with any knock interpreter, it's guaranteed to crash. Like, it's part of the spec. So, in the knock spec, you don't see any data type for error, right? Or crash or anything like that. All there is nouns. So how do you express a crash? And the answer is it is a trivial infinite loop. Trivial meaning there's sort of nothing there. So there are a bunch of places in the knock spec where you'll see, star A, right? So star A on the left produces star A on the right, right? So at the very end of the knock spec, it says this. And so that means that if you give knock anything other than a valid formula to run on a subject, then it's defined as an infinite loop. Like, that's what it's supposed to do. It's just supposed to call itself again. And so that's a simple enough thing to notice that, like, it's just the way the metacircular knock interpreter can catch these errors, which, by the way, is the same way that the actual knock interpreter can also catch these errors, even at the top level, even though that's outside of the spec, but it can still do it. It's just because, the metacircular knock interpreter, mock, it says, hey, is the formula a cell? First of all, if it's not, then okay, that's a zap. That's an error, right? Okay, we're not going to be able to run. So there you go. Or then, okay, well, if it's it is a cell. Is the head of it a cell? All right, well, then we have two formulas. So it's just, that's an autocons, as I described. So go ahead and run both of those formulas, combine the results into a cell. Or is the head of this an opcode, 0 through 12 for mock, 0 through 11 for not mock, right? Well, then, okay, go ahead and run whichever one it corresponds to. And if it's not, then, okay, it's an invalid formula, so crash, right? But when it's run in metacircularly, we don't actually have to crash the event. That's just, one of any number of outcomes. And so we actually produce, when you run not code metacircularly, we can catch the errors. And so whenever it runs, it produces a pair of 0 or 1. And so it either produces a pair of 0 and the successful result, or it produces a pair of 1 and some information about what went wrong, right? Some failure information, stack trace, which is just a log of what the thing tried to do and failed. So when we run an app, we actually catch these errors, and we also give it a scry handler. So Arvo, the kernel, gives the app this sort of opaque function that it can run to using a special opcode that only exists in virtual knock, that it can use to access this immutable namespace. And the beauty of this is that instead of running this metacircular interpreter in knock, that function, mock, is jetted. There is a jet that corresponds to it. And so when some knock code is running and it calls mock, the interpreter sees, I have a jet for mock, so I don't need to run the knock code corresponding to it. And so what it does is it says it jets it with the interpreter itself. So the interpreter actually just knows how to run mock, and so it jumps into a new sort of memory arena. Don't worry about that if you don't know what it means. But basically, like, it basically just tracks a number of like how deep it is, and sort of runs this in a different part of memory, and then, but it's just sort of another instance of the interpreter itself. And what that means is that you can nest these calls to mock, like you can call mock, and then from within the code that's called by mock, you can call mock again on some other code. And you can do that as deeply nested as you want. And each time, that'll just call back into the interpreter with no interpretation overhead. So it doesn't get slower. So you can be, 6 or 7 virtualization layers deep, and the code runs exactly as fast as it did at the top layer. So this idea of a metacircular interpreter has been around since, I think, the 50s. I mean, it's a very old idea from Lisp. And they use it for a lot of stuff. There are a lot of times, Lisps will sort of bootstrap themselves, starting from a very minimal set of functions, and then, minimal language definition, and then use a metacircular interpreter to add pieces of functionality to the language, just like we added this knock 12 opcode, and the ability to catch errors, in virtualized knock. But without jets, every time you go deeper into this virtualization, every operation that you run gets slower, because it has to be interpreted, n times if you're n layers deep. So this is one of the really important uses of jets in Urbit, is to handle this form of metacircularity. And so we do full speed metacircularity, and as far as I know, Urbit is the only system that can actually accomplish this. So this is why we run apps this way, because it's not any slower. It just gives us an extra piece of functionality. So that's Hoon, right? Hoon is a language that compiles down to knock, so it's convenient for programmers. It has, 100 little sort of patterns that you can do that are categorized by so each one is identified by a rune, which is a 2-letter or 2-character symbol. Those are the only symbols in Hoon, by the way. Everything else is actually text, and so so you can very quickly know whether what you're looking at is a rune or just a name for a part of the tree. And then so Hoon gives you these, this sort of syntactic sugar for doing common knock patterns. It lets you name all the pieces of the tree, so you don't have to remember numbers. It gives you data types, so it'll actually check type safety. It'll automatically generate functions that let you coerce external data to a valid type and crash otherwise. It gives you this paradigm for building more complex programs out of simpler programs. I'll get into that more when I talk about Arvo and Clay, which is our file system. And inside of Clay, there's a build system called Ford. And that's really where we build most of the applications. And so that uses that vase pattern, that sort of vase 2-step, vase building pattern, where you say, okay, first take, you have vase of subject and you have some Hoon text, and you do a 2-step thing where first you take the Hoon text and you compile it against the type of the subject vase. That produces a pair of the type of the result that you'll get out of that, and some knock code that you can run against the value in the subject vase. So then you run the formula against that subject using raw knock. That produces the raw knock of the result, and now you have a vase of the result. So you go from subject vase to result vase. And right, so describe that a little bit, and I'll describe that more or how that gets used more when I talk about Ford and Clay. But actually, and also when I talk about Arvo, because Arvo uses that pattern itself pretty heavily as well. And so that's one of the main facilities that Hoon gives you. And then it also gives you the ability to run other Hoon code to metacircularly. And so this is a really convenient way to run user space code or other code that you expect might fail, or code that you want to have sort of limited, secure access to the Urbit namespace. So that's more or less Hoon in a nutshell. I'm happy to answer any questions you guys might have about it, or do some more in-depth descriptions of Hoon. This is Hoon at a very high level, but I would say that if you're learning Hoon, there's going to be a fairly steep learning curve at first. I highly recommend learning Nock before learning Hoon, because it makes a lot of the design decisions of Hoon make a lot more sense. And a lot of the runes, when you encounter them for the first time, you'll say, okay, that's just a Nock 6. All right, what col is just a Nock 6. What dot is just a backward Nock 6. Tis gal is just a backward Nock 7. Tis gar is a forward Nock 7. Tis lus is a Nock 8. Tis faz is a Nock 8, etc. And so, all these things, they're a lot easier. You have to, there's a lot sort of less information that you have to remember when learning Hoon in terms of Nock. So I highly recommend it that way. And in general, there's going to be a fairly steep upfront cost, because the system is very different from other systems that you might have learned. And there's a fair amount of syntax to it. And there's there are a bunch of concepts that you have to internalize in order to understand it. But then once you internalize it, once you get over that steep initial learning curve, it's pretty much smooth sailing. There's a little bit of weirdness with wetness, but you don't encounter it too often. And they're like, the real trick to Hoon is that, like most of Urbit, it just doesn't do that much. It basically just gives you a little bit of structure around compiling to Nock. So that's Hoon in a nutshell. And I was going to describe Arvo and Veins in this episode, but I ran out of time, or I ran out of steam mentally. So next episode, I'll describe the Arvo kernel, and we'll see if I get through that. Then I'll just also describe the veins, which are the kernel modules. And so that will rely pretty heavily on this description of Hoon. Thanks for listening.